Hi everyone, my name is Victoria and I'm gonna start our presentation by introducing our team and giving you a brief overview of our project, what it's about, why we created it, and the problem we aim to solve. After that, we will guide you through the application's design and key features. Our project is called Medication Navigator. It's designed to make complex drug information more accessible for everybody users, especially those without technical or medical backgrounds. Here's our team. Each member brought a unique skill set to the project. And let's start with our team lead, Dmitry Kolomeits. His work was focused on backend infrastructure, managing database, VM, domain, Docker containers. He integrated Fire and Azure AI services and built a RAG-based summarization system. Nikolai Skrabin. Nikolai led the UI development by building core pages with routing and styling connected front-end to the backend and enhancing user experience with the search, pagination, and error handling. Victoria Clements. I handled backend logic, set up the fast API application with Azure SQL database and Fire integration. I developed endpoints for searching by ingredients and conditions using Fire, RxNorm, FDA data, and managed data parsing. It's also worth to mention that while each of us had a primary area of focus, we collaborated across roles and supported each other domains when needed. So why we built this? Major sources like OpenFDA, RxNorm, RxNav provide a lot of useful drug data, but they are mainly designed for developers, healthcare professionals, or companies that need access to API. These platforms assume a certain level of medical or technical background, which creates a gap for everyday users. Also, most current custom tools focus on brand or product names, which means many people don't realize they can switch to an equivalent medication that better accommodate their budget or preferences. People dealing with a symptom or condition may want to explore other medication with different active ingredient that offer a similar effect, maybe something milder or stronger, depending on their needs. But without clear, accessible tools, it's hard for user to compare these options. As a result, people end up relying on brand names unaware that some alternative with the same effect exist. This lack of access or information can lead to higher costs, fewer choices, and even poor medical decisions. That's why we built a tool that shifts its focus to what really matters, the active ingredients and treatment effects. Our approach. Our approach was inspired by real life experience, like going to the pharmacy and being told, sorry, we don't have the brand. So we built our app to guide users through those situations. Instead of focusing on brand names, we focus on what actually matters, the active ingredient and treatment purposes and side effects. Our tool allows users to search for medication based on symptoms or active component and then see a structured summary of alternative options. So the goal? To make medication search more accessible, more affordable, and help people make informed decisions.
Hi, my name is Dmitry, and I'm here to share the research that we had to make to implement our application. So we basically had to explore three components. The first one is Fire, that includes Fire servers, Fire specification, Fire resources, and API. The second one is RxNorm database and its API. And the last one is OpenFDA database and the API. As for Fire, we end up using Fire medication resource because it contained all the information we needed: active ingredients, dosages, IDs, and also doesn't require authentication because it's not personalized. We also had to explore how to make efficient search for medications by active ingredient. One of the challenges that we had to deal with is that public Fire servers, they are unreliable, sometimes they're buggy or very slow, and they're also empty. So we also had to find ways how to migrate, how to create medication resources and way to find data for it. So we end up using RxNorm database to create medication resources to pre-populate Fire server. So as for RxNorm database, it was efficient, but the main challenge was to figure out what term types to use when searching for entities, because there are a lot of different acronyms for those. It's not really clear what they mean, and it's not always clear what to use. Another source of confusion was with diseases, because it's not really clear what disease is. Is it a symptom? Is it the name of the disease? Is it the name of the illness or condition? So it ended up being a mix of all of those. And it's also not complete. So you cannot find everything. Well, you can find something. The main challenge we had to deal with was that it was loosely structured. So we had to rely on this, on the integrated substring search that led to undesired behavior, like you can find medications to treat rats or pregnancy or elderly. And it's also incomplete. There's still many ingredients searching for which you cannot find any medications. Thanks.
Hi, my name is Nikolai and I'll demo the app. The landing page displays a search bar with three options for the search on the left. To search medication by ingredient, select the option and enter ingredient, then click the search button. I'll search for ibuprofen. The medication by ingredient view displays the result table that includes columns with medication, brand name, active ingredients, and conditions. Above the table, there are two accordion buttons to display warnings and usage of the ingredient. Click to see the info. Also, users can access warnings and usages by clicking right on the active ingredients names in the table. Click to navigate to the details page. Details page has the same usage warnings buttons. Click to see the info. To search medications by condition, select the option and enter condition. I'll search for fever and press the button. The medication by condition view displays a table that includes columns with medication name, purpose, active ingredients, and drug effect. It has two accordion buttons, usages, and warnings. To search ingredients by condition, select the option and enter condition. I'll search for cough. The ingredients by condition view displays a table that includes columns with ingredients and links to search medication. Click on search medication to navigate to the medications by ingredients view. After that, you can explore the medications or get back to the previous page. Thank you for watching.
Now let's talk about the backend side of our project. We built it using Fast API, which was a great choice for us. It's fast, modern, and easy to use. Plus, since it uses Python, our team's native language, development was quick and smooth, interactive documentation, which was big help during testing and development. Because our project is relatively small, we kept the backend structure simple and clean. First, we have main by file is the entry point for our application. A separate route modules handle the API endpoints that connect to the front end. There is a Fire client Py and a couple of scripts for migrating and retrieving medication data from the Fire server. We also have model Spy and DB util Spy to define our database tables and handle related logic. Internal processing is done through util Spy. And finally, RAG-utils defines a RAG summarizer class which uses Azure's chat completions client to generate short AI-based summary of medication warning and purposes. This structure keeps things modular, scalable, and easy to maintain as the project evolves. Alright, so the core endpoints we implemented were medication by ingredient and ingredient by condition, medication by condition, and also medication summary, which returns group medication information like warnings and purposes. Alright, so our standard workflow starts with retrieving the Rx CY from Rx norm database. We then try to find the corresponding medication on our Fire server. If the medication isn't already there, we trigger an auto migrations here, pulling data from Rx norm, transforming it into a valid Fire medication resource, and upload it to our server. Once the medication data is available, we process the medication data and retrieve related condition that the active ingredient can treat. The final result is returned to the frontend in a structured format. To boost our performance, we use caching with the Azure-hosted database, where we store frequently used ingredient and condition codes. This reduces API calls to external services and speed up related lookups. Overall, the backend is designed to be modular, fast, and responsive, ensuring a user always gets accurate and relevant results without frustrating delays. Thank you.
It's Dmitry here. and I wanted to quickly touch the deployment and the RAG summarization component. Starting with deployment, when user opens the website through this domain is basically connected to this virtual machine. The virtual machine lives itself within this Azure resource group. The Azure resource group contains all the necessary resources for the app. Mainly, it's the Fire server, which is the Azure Fire service that we use to keep all of the data in the Fire format related to medications. Our SQL database that is there to speed up the request response cycle, our virtual machine with the public IP address, and our Azure AI gateway to the LLM that we use for summarization. The app on the virtual machine is deployed via Docker Compose. Docker Compose spins up 3 images. The first one is front-end build, so this container is just spin up to build front-end files, and then it goes down. The second container is the backend container, so it's spinned up and lives there and hosts the backend application. The third one is Nginx container that navigates the deployment and routes the request to either backend or serve static files for users. I also wanted to quickly touch the RAG summarization component. So RAG stands for Retrieval Augmented Generation, and let's take a look at the retrieval part. So every time the user wants a summary for a group of medications with a common ingredient, we retrieve the warnings for all those medications and purpose labels. And then we feed it over to LLM through this gateway. And this is just the name of LLM, but we can use any other model. We're using this because it's free. Along with this set of instructions that basically guides the model about what type of response the user is expecting. We also cache the response from LLMs for the ingredients for which we already retrieved the summary. Since the summary is pretty static, there is no reason to request the same summary over and over again. Thanks for your attention.
In its current state, the application is functional and provides a cleaner, more user-friendly interface for exploring publicly available medication data from OpenFDA and RxNorm. It effectively merges data from both sources into a unified, organized view and helps educate users by summarizing groups of related medications. That said, several areas could further improve the user experience. One key feature we identified is type hinting. Users often struggle to guess the correct medical terminology when searching for medications. For example, someone with a cold may not find useful results by searching for cold, which isn't a searchable condition, but could find relevant medications by searching for related terms like fever, cough, or nasal congestion. A system that guides users toward searchable terms would greatly enhance usability. Another improvement would be increasing transparency about how the app works. Users may mistakenly assume that the information shown is curated or specific to our application, when in reality it's pulled directly from public databases. Clarifying that the app is a search interface on top of OpenFDA and RxNorm could help set accurate expectations, especially when certain search terms yield no results due to database limitations rather than app failure. We also intentionally avoided altering or reshaping medical data, instead choosing to display it as is. However, this revealed another challenge. Relationships, such as may-treat between ingredients and conditions, often imply secondary or indirect effects, not necessarily the ingredient's primary purpose. Additionally, some minor inconsistencies remain. For example, ingredient names like naproxen versus naproxen sodium are sometimes used interchangeably despite being technically different. OpenFDA also lacks structured condition data, so search relies on parsing unstructured text in drug warnings and descriptions, leading to occasional noise or misleading results. In summary, while the core functionality may seem straightforward at first, working with complex and inconsistent medical terminology and integrating data across two large, loosely structured datasets quickly reveals the deeper complexity of the task. Nonetheless, we believe the project successfully lays out a solid foundation and could serve as a useful tool, especially with future improvements in search assistance, clarity, and data refinement.